Okay, well, good morning, good afternoon, good evening. Welcome wherever you are joining us um, for the 29th, the 19th of September edition of the OSMU 2025 lecture, which is being given today by the founder of the seminar, my friend Tejinder Singh of the Tata Institute of Fundamental Research in Mumbai. Tejinder got his master's degree from IIT Delhi in 1984 and then went on to get his doctorate from the Tata Institute for Fundamental Research in Mumbai in 1989. He's been a faculty member of the TIFR, I should say, ever since. I think that's correct. But he's also held visiting positions in Trieste at the International Centre for Theoretical Physics, and is currently visiting professor at IUCAA. I'm sorry, I always get that wrong. IUCA, where in fact he's been visiting professor, I think, since 2022. Is that right, Tejinder?
23.
23, right. Okay. He has been extraordinarily fertile in his research, both in the depth and breadth of his research, and has contributed many original and fruitful ideas to discussions in quantum foundations and programs towards the development of quantum gravity. In fact, I hadn't realized until just looking through his list of publications yesterday how extraordinarily broad his interests are, because I saw that he'd contributed a very interesting essay to the FQXI essay competition a year or two ago about cognitive aspects of the foundations of mathematics, which is really very much more my neck of the woods in history and philosophy of mathematics, which I was reading with great interest. But today he's coming back to a topic which is of great interest and which he's written quite a considerable amount about, which is the role of the exceptional Jordan algebra in programs for the unification of physics. And in this today, he's talking to us on fermion mass ratios as derived from the exceptional Jordan algebra. And over to you, Tejinder.
Thank you. Thank you, Michael. Very kind of you with that introduction. I hope you can all hear me clearly. And this is the tagline that I want to emphasize today, that octonionic triality explains the origin of three fermion generations, but breaking of this octonionic triality is what gives rise to the observed mass hierarchy and mass ratios. Right. So this is the end product of what we think we have found in this work. I'll explain so the job of the talk is to explain where these ratios come from. So we have 9 fundamental charged elementary particles, the 3 charged leptons, electron, the muon and the tau lepton, the down quark family, down, strange, and bottom, and the up quark family, up, charm, and top. And the claim is that the square roots of the mass ratios are more fundamental than the mass ratios themselves. And in terms of this theoretically derived spectral spread delta, which is square root 3 by 8, these are the theoretically derived mass ratios. They are closed fractions which depend on delta as given here. So up quark to the electron is 2, down quark to the electron is 3, and then strange quark to down quark is this fraction, which interestingly is equal in this theory to the ratio of the tau lepton to the muon. So you see 1 plus delta over 1 minus delta, and the decimal values are given here. So this is a prediction of the theory. This is a cross-sector prediction. The quark mass ratio strange to down is equal to lepton ratios tau to muon. I'll try to justify this. Then this for bottom to strange, muon to electron, charm to up, and top to charm. the agreement with so these are predictions at the electroweak energy scale just after electroweak symmetry breaking. So using standard quantum field theory, one can estimate what are the corresponding ratios at the electroweak scale as observed experimentally. So you can compare how we fare against experiment. The match is not exact in most cases, but within few percent. And we believe that this is interesting enough for us to look further into uh, why these small percentage level deviations are there compared to the theory. So I just wanted to remind that we found these same ratios a few years back in this paper with my co-authors. So what I showed you here, this table is actually the same as this table, except that the one on the previous slide is written more compactly. It is the same delta. I've realized that the ratios look cleaner if you compare neighboring generations, like second generation to the first one and third to the second, rather than writing third in terms of the first. Then it looks a little more complicated, but it looks simpler if I write, for example, bottom to strange, because one factor cancels out and this simplifies. And it's good to introduce this short form delta is square root 3 by 8, so the whole thing starts looking cleaner. So why did we write another paper if we already had these results? I think we found some additional insights and justification for why the ratios arise this way. That's why this fresh perspective. Right. I try to keep you in the loop throughout as we go through the mathematics. And here is the big picture. At the electroweak scale, unification scale, we assume that there is unification above the electroweak scale. And the unified theory is given by two copies of the exceptional group E6, which for clarity of notation, so E6L cross E6R, L and R will eventually become left-handed and right-handed, but not at this stage. So as you know, E6 is the norm determinant preserving group of the exceptional Jordan algebra, denoted X, which is the algebra of 3 by 3 Hermitian matrices with the complex octonionic entries. X, Y, and Z are complex octonions, and Z bar, X bar, Y bar, and Z bar are their joint conjugates, complex as well as octonionic conjugates. So prior to the electroweak symmetry breaking, which will also be what we call a trility symmetry breaking, we have two identical copies of the exceptional Jordan algebra, also called the Albert algebra. J3OC, some J3OC, there are two identical copies of J3OC, which each has a uh, structure preserving group E6. So two copies of E6. Then the branching and the accompanying spontaneous symmetry breaking, which we assume and which we propose, is what is known in the literature as the trinification of E6, which means each of the E6 branches into three copies of SU3. Here for the first copy of E6, and here this arrow shows the second copy of E6. How do we interpret the three SU3s? The first E6, E6L is the standard model. SU3 color for QCD, SU3 flavor, which is what will give the mass hierarchy, flavor left, and SU3L branches into the electroweak sector, which breaks to electromagnetism. That's standard electroweak. But now coming from E6. The second E6 is what is new. We have a SU3 color prime, which you could call strong gravity, is the dark sector analog of Q3. But for the purpose of this work, we don't gauge it. We keep this global, that is safer. SU3 flavor on the right hand side. So the left flavor will give 3 generations on the left hand side. The right flavor will give 3 generations on the right hand side. SU3R corresponds to SU3L, and that branches as SU2R cross U1Y prime, which again undergoes a symmetry breaking to give us what we call dark electromagnetism. And SU2R broken is the precursor of general relativity. So since we are not gauging SU3 color prime, we have one new gauge force, which we call dark electromagnetism, and that plays a pivotal role in understanding mass ratios. So after the trinification, so what happens is triality symmetry is broken down to flavor symmetry. I'll explain that more. The two Albert algebras now become distinct because the vacuum chooses one eigenaxis on the left and a different one on the right. This U1, the first U1 is U1 electromagnetic, and this protocharge P naught from before symmetry breaking, it was same on left and right, but now this will become electric charge. As we understand it in the standard model, it will become electric charge. This is U1 electromagnetism giving rise to this electric charge, and 3 generations which will now obey flavor symmetry. On the right hand side, we have this U1 dark electromagnetism, where now the quantum of charge is not electric charge, square root of mass. Okay, so that's the difference between UN electromagnetism and UN dark electromagnetism. These are eigenstates of electric charge or flavor eigenstates. On the right hand side, we have eigenstates of square root of mass. And since the vacuum selects different axes for the first E6 as compared to the second E6, the flavor eigenstates are not the same as square root mass eigenstates. And when looked at from the point of view of the left hand side is when these mass ratios start looking weird and correspond to the table that I showed you, and which is what is the origin of the mass hierarchy in this theory. This breaking of triality symmetry down to flavor symmetry is claimed to be the origin of the mass hierarchy. So if you feel like stopping me, please stop anytime during the talk if you have a question or a comment. Okay, so this is the plan of the talk, divided into 4 parts. First, explain in more detail the E6 cross E6 unification and the trinification of E6. Then after a triality symmetry breaking. What is triality breaking? The trinification is the same as triality breaking. Triality breaking, flavor symmetry, and left hand and right hand states for 3 generations. In the third part of the talk, we start to build towards deriving mass ratios. I will use this so-called symmetric cubic irrep of SU3 and talk of something called the Dinkin swap. And in the last part of the talk, we propose a so-called minimality principle to derive the mass ratio. So these are, I'll keep you informed which part we are at and try to keep the big picture in the forefront so that we don't get lost in the mathematics. Okay, so this is the first part of the talk. Uh, Prior to the electroweak scale, let us assume a left-right symmetric unification through E6L cross E6R, where L and R are same before symmetry breaking. We know that spinate is a subgroup of F4, which is a subgroup of E6, and spinate has this famous outer automorphism S3, the permutation group of three objects. And various researchers have argued that this so-called octononic triality is responsible for the existence of three identical fermion generations, because because of this symmetry called triality, spinate, as we know, has three inequivalent representations, two spinor and one vector representation. And we will, for the purpose of this talk, take it as a given, as shown by or argued by various people going back to Gunaydin and Gursi. Then I think Todorov, Pierre Ramon, many names I might be forgetting. And then in more recent times, Garrett Lisi, Cole Fury, Niels Gresnick, and through CL8 recently Quinta. And I'm sure there are some names I'm skipping, forgetting. They have argued that the triality of spinate is what is responsible for there being three fermion generations. So we agree with that. But triality does not give the mass hierarchy. Triality gives three identical generations which are indistinguishable. And these three generations belong to the Albert algebra. And now let us construct their states via three isomorphic copies of CL6. So we appeal to this Clifford algebra and make two copies of J3OC, which is a 27-dimensional representation of E6. And what will each of the copies look like? It will have a so-called proto-charge P naught, which we assume to be a real number. X nu, Xc, and Xs are complex octonionic states. So I've just pulled out the trace to show both copies of LNR in like this. They're both identical. And the three states have equal norm. And it will turn out, and also can be argued, that the real part of this triple product actually is zero. This is the triality symmetric state before triality breaking, when we have E6 cross E6 unification. So two copies of this. These states are G2 covariant. You can make a triality transformation by some element G of G2 on each of these states, and that would be fine. And S3, this outer automorphism, permutes these three states amongst each other. Okay. Now, how do we construct, let's say, one generation using CL6 and complex octonions? Let's remember, we are still in the symmetric phase. Symmetry has not been broken. But this methodology, for example, in recent years was nicely developed by Cole Fury. But in my language, that is what Cole does is after triality breaking. So we now see what's the corresponding uh, analogous scenario before triality breaking. Select a temporary complex axis IE7 amongst the seven octonionic directions. And this IE7 is not fixed. you can make G2 transformations on it. Define the so-called idempotent, which is identified with the Dirac neutrino as half of 1 plus minus IE7. Then define creation and annihilation operators using the other 6 octonionic directions. This should be familiar if you have seen how a one generation of standard model fermions is constructed using CL6 and octonionic chains. A and A dagger obey the standard anti-commutation relations, and the vacuum is annihilated by the A's. So this is a minimal left ideal for constructing one generation of states, but prior to triality breaking. So this is what those states would look like. There are 8 of them in the minimal left ideal acting on the Dirac neutrino. And if you like, we can look at a SU3 in G2 because we have selected a E7, and these 8 states give this decomposition under SU3. This is familiar, 3 bar 3. So there's a 3 bar, there's a 3, and there are these singlets. But it's very important to remember these are not elementary particles of the standard model, because for that I need to be able to define electric charge. Electric charge is related to the fixed direction, here IE7, but our IE7 is not at this stage an invariant. We can, even after making one selection, we can make G2 transformations on it. So important. Before symmetry breaking, there's a full internal symmetry is G2. After symmetry breaking, this will become SU3 flavor. But before breaking, the number operator related to this direction IE7 is not an invariant. There is no U1. So this is very important to remember. We have triality symmetry related to the full spinate and G2 in E6. And we do have this kind of a 8-state basis, but there is no concept of electric charge which one can associate. This P naught, which I was there in, right, there's no way to fix this P naught. It is arbitrary. So there are no families. There are no electric charge quantization. There are no families. There are 3 identical generations where P naught is not fixed. Right. So I have a CL6 related 8-state basis for each copy of the Albert algebra before symmetry breaking. We can construct antiparticles which live in the conjugate ideal obtained by complex conjugation and by this swap. And as I said, the choice of the axis I, which was IE7, is only a writing aid to help us visualize how one generation is defined. But there is no charge quantization prior to triality breaking, and charge quantization will now emerge subsequently once triality is broken. So we have one generation. We want 3 generations. So let's set that up. 3 identical generations before triality breaking. The triality S3 acts on the creation triple by defining these 3 cycles. So suppose a one generation, let me define a 3-cycle map. 1 goes to 2, 2 goes to 3, 3 goes to 1. So what do? You take the creation and annihilation operators for the first generation, map those to the second generation. Say that the second generation A's and A daggers are now those of the first generation, and the second generation's a pi-square map on the first generation gives you those for the third generation. This is what is shown here. So A2 dagger A1, A2, and A3 for the uh, second generation by a cyclic map, and by a pi-square map those for the third generation. And the 8 basis states for generation 2 and 3 are obtained by replacing. So this map, if you apply here for every I, if you go to the second AI for the right, I is 1, 2, 3 stands for these three generators. Uh, Map the first generation to the second and the first to the third by pi square, and we will get one copy of CL6 for each of the three generations, and we can now put this in the Albert algebra. And so this is, sorry, here I'm just saying there's an equivalent different way of getting three generations. If you have one generation, you do a G2 action on the octonunic directions for that generation, and you could, this is just an equivalent different way of getting three generations before triality. So if we choose to keep IE7 fixed, then our idempotent will stay fixed, but we can transform it if we wish. And in this way of looking at things, the second and third generation are obtained by making this kind of a cyclic map. E5 goes to E3, E4 goes to E1, and so on. And you can again write three identical isomorphic copies of CL6 before triality breaking. As I said, either you do what I showed in the previous slide, or you do what I showed here. And all three generations are S3 or conjugacy class equivalent in the unbroken theory. Okay, now so I have three generations before triality breaking, and one can interestingly solve a eigenvalue problem. The neutrino is defined as this idempotent omega plus. It's a Dirac neutrino because there is a left-right symmetry. We are not allowed to have a Majorana here. For the chosen states that we just constructed, write the Albert algebra two copies. P naught is indeterminate. So this R naught is not needed. There's no R naught here. And the states that we just constructed, you in the Clifford algebra have this norm 1 by 4. They satisfy this condition. The characteristic equation of this Albert algebra of 3 by 3 matrices is as follows. It's a cubic. This goes back to the work of Tavian Ray and Corinne Minogue, showing that there's a eigenvalue problem in the Albert algebra obtained like this. The trace is 3p naught. This quadratic form is given by this definition in this cubic equation. The determinant has this definition shown here. So we have all the ingredients. Let's put that in. We get a spectrum of real eigenvalues for the Albert algebra given by P naught minus delta naught, P naught and P naught plus delta naught, where delta naught square is 3 by 4, but P naught is indeterminate. So we still don't have families, we don't have charge quantization, but it is important to keep this in mind because this spectrum is going to play a crucial role in mass ratios emerging. So we'll have a spectrum after symmetrality breaking for the left-hand sector, and we'll have a spectrum for the right-hand sector, which are emergent from here. Right. Since we have the spectrum, we have the eigenvalues. We can diagonalize the Albert algebra matrices X in what is known as a Jordan frame. This is a set of three primitive, mutually orthogonal idempotents. These are matrices in J3OC, which will give us a basis. So the spectral theorem in this context is that for any x belonging to J3 or C, there exists a Jordan frame in which I can write x in this diagonal form where lambda 1, lambda 2, lambda 3 are the three eigenvalues in this spectrum shown here. The pi can be the matrices pi are related to x and the eigenvalues as shown here. What is important is that triality permutes the idempotence P1, P2, P3, and the spectrum of eigenvalues can be attached to the frame in any order. I cannot say that lambda 1 belongs to P1, lambda 2 to P2. I can apply triality to it and float, the lambdas float across the piece, which is what will not happen after triality breaking. So here, cannot talk of eigenvalue ratios in a physically meaning way. Suppose you mass ratios will arise from ratios of these eigenvalues, but here they have no meaning. So like, suppose I have these three eigenvalues, lambda 1, lambda 2, lambda 3. I can make what will come again and again, a symmetric cube, namely degree 3 monomials from lambda 1, lambda 2, lambda 3. Given three eigenvalues, I can make 10 degree 3 monomials, the pure ones, the mixed ones, and the democratic one, lambda 1. But suppose I want to make ratios from here which obey triality. I cannot do things like lambda 1 by lambda 2. It can be shown that the only triality invariant ratios which can be made from these eigenvalues are these three ratios shown here. Obviously, they don't carry any information about mass ratios or charge quantization because P naught is not fixed. So ratios like this are not triality invariant and require the triality symmetry to be broken, which is what will be the trinification of E6. So to remind ourselves, we are still prior to the triality symmetry breaking. We have a spectrum and we can think of making such ratios, but right now they are not physically meaningful. But it is these degree 3 monomials from which we will make mass ratios after triality break. Okay, so now we move towards trinification. If you like, I can stop in case there are any questions or comments. I should proceed, Michael?
Sorry, Tejinder, I was silenced. Yes, I think so. Unless there are any questions, it's all been quite clear so far.
Okay, thank you. Thank you. So as I said, now we will do a symmetry breaking, which leads to the emergence of the standard model through this so-called trinification. The first E6, now E6L and E6 are going to become different. The left-right symmetry is broken, electroweak symmetry is broken, triality symmetry is broken, assumed to all break concurrently at the electroweak scale. So we get the standard model SU3 color, QCD. One SU3 will be used for flavor, namely to get 3 generations. The third SU3 breaks to give the electroweak sector. Then on the second E6, we have a new SU3C prime, which we will not gauge. SU3 flavor for the right-hand side, and SU3R breaks to give general relativity, which comes from SU2R, which we won't go into in this talk, and a U1Y prime, which after the right-hand side SU2R breaking becomes this U1 dark electromagnetism. More on this U1 DEM soon. So left-hand side QCD and the electroweak sector now can define electric charge from U1EM. So we'll see more of this. Flavor symmetries SU3F for the left and right give rise to three generations and mass hierarchy left over from triality breaking. So the SU3 flavor symmetries are left over from the triality coming from spinate's outer automorphism G2. So now we will select a specific axis which cannot be transformed under G2. So that's the breaking of triality. Right hand sector, strong gravity, not gauge kept global, and the gravidem sector shown here can now define square root of mass from U1dm. So more on this soon. The charge, quantum of charge associated with this will be so-called square root of mass in contrast to electric charge on the right hand side. The single pre-breaking center. So pre-breaking, the spectrum was centered around P naught. We have P naught minus delta, P naught and P naught plus delta are the three eigenvalues. Now, P naught will pick up two different centers. On the left-hand side, it becomes electric charge. On the right-hand side, it becomes square root of mass. So visualize here, define P naught as e to the lambda. Then electric charge will be e to the lambda plus sigma. Square root mass will be e to the lambda minus sigma, where sigma is what is selecting the new center now. P naught becomes q on the left hand side. It becomes square root of mass on the right hand side, such that P naught square is q root m. Okay? Right. So just a quick word before we go on to the second part of the talk. Number operators and the two emergent U1. So there's no U1 before. After triality breaking, pick complex axes IL and IR. So pick two different axes which are selected by the vacuum. There was no physical choice before triality breaking, but now the vacuum picks up a definite choice. On the left-hand side, given IL, define once again these creation annihilation operators on Cl6L, on Cl6R, and these are the corresponding number operators. Q will be defined, this is in the sense of Paul-Fury's work, 1/3 of the number operator for the left-hand side is the electric charge operator, gauged as U1 EM on the left-hand side. This is the square root mass operator, defined now as 1/3 of the number operator on the right-hand side, gauged as U1 dark electromagnetism. Both these number operators originate from the pre-breaking number operator N naught, but now they are defined only after picking, N naught was defined only after picking a temporary axis. N naught, the number operator before breaking was not physical. It transforms under G2. There is no fixed U1 here, but after triality breaking, the vacuum fixes IL and IR. N naught is giving rise to the left-handed number operator and hence electric charge by a certain select unitary transformation. Same, the right-handed number operator, which is distinct from the left-handed one, is being picked by a choice of the vacuum. Q equals NL by 3, the left-handed number operator and the right-handed one are the same underlying counting operator seen in the two symmetry selected frames. So now symmetry breaking selects two frames, one on the left-hand sector and the other on the right-hand sector. And this is how charge and square root mass emerge, because we have a U1 now, which we have two copies of U1, which we did not have earlier. And because these two copies of U1 are distinct from each other, that is how the mass hierarchy will arise. Okay, so moving now to the second part of the talk, triality breaking, flavor symmetry, and left-handed and right-handed states for 3 generations. We are going to repeat the construction of 3 generations the same way like we did with the Albert algebra before triality breaking. But now the triality symmetry is restricted to flavor symmetry. We'll have chosen a specific axis which we cannot move around. Very interestingly, we will assume the neutrino to be Majorana. Why? Because it turns out only then we get the correct mass ratios. If you continue to, before symmetry breaking, it was Dirac neutrino. If we continue to assume it to be Dirac, it can be proved that we won't get the observed mass ratio. So this is a prediction. The neutrino is Majorana. It should be confirmed in the lab. And if not, then our theory is wrong. So we predict that the neutrino is Majorana. And we proceed to find 3 generation states, both in the left-hand sector and in the right-hand sector. Let's start by doing it for the left-hand sector for 1 generation. So this you are familiar with. Let's choose an axis E7. Now this is a vacuum choice. Unlike before, I cannot make G2 transformations on it. This is fixed. And that is what will define my SU3 flavor, because IE7 will determine the electromagnetic U1 EM, and SU3 flavor will commute with this. So once fixed, I cannot move at this axis. Assume neutrino to be Majorana, and the Dirac neutrino form was this. After breaking, the Majorana neutrino is defined like this. So I denote it with the symbol M, plus for the particle minimal left idle, and then minus for its conjugate. So we repeat what we did. Build the 8-state basis Cl6 by acting on the Majorana idempotent for 1 left-hand generation, and calculate eigenvalues of Q equals n of n by 3 for these states. So we have a U1, its number operator. We'll call it the electric charge operator. Q, the electric charge operator, is 1/3 of the number operator in this Cl6 basis. Once again, we get these 8 states like we saw before. But now I can calculate this charge operator for each of these 8 states and find its eigenvalues for each of these states. For nu m, Q is 0. For this 3 states, D1 bar, D2 bar, D3 bar, Q is having an eigenvalue 1/3. For U1, U2, and U3, it has eigenvalue 2. So this is really Cole's work. So I am now embedding this work in the full setting where triality is now broken. Earlier it was not broken. And for this singlet, the Q eigenvalue is 1. So we have singlets of SU3 color. This Majorana neutrino and E plus are singlets of SU3 color. D1, D2, D3 are anti-triplets of SU3 color. And U1, U2, U3 are triplets. So justify, and they have the correct values of what would be standard model electric charges. So now I'm justified in saying that 1 generation of standard model particles has emerged. The first one is the neutrino, then these 3 are anti-down quarks, then up quarks, and the positron. And under SU3, this has the standard decomposition. This SU3 flavor, now it is fixed. I cannot play around with it. So this is what we mean by saying that the emergence of this U1 restricts the triality symmetry to a flavor symmetry, and antiparticles can be constructed as before. The choice of the axis IE7 is now not a writing aid. Charge quantization emerges after triality breaking, and we have one generation of left-handed standard model fermions under the unbroken symmetry. And if you follow Cole's work, her PhD thesis, and later, this is precisely what she does. But now we bring variations on it, like we have a pre-triality stage. We are working with a Majorana neutrino, and we will construct analogous right-handed fermions where the U1 number of the U1 quantum of charge will be square root of mass, not this Q. Okay, now we can construct states for the second and third generations and again put them into the Albert algebra and once again find eigenvalue spectrum. So this, how do I construct second and third generations? I should use SU3 flavor symmetry transformation. So why are there three generations? That has been determined by triality. So with that we take as given now. There are three generations. Triality broke, but it kept those three generations. And how to get the second and third generations? Keep one direction fixed, say E1, choose one core color, say red, and get second and third generation states by applying the following map on first generation states. Why does this map work? Actually, this is a SU3 flavor transformation, as can be easily shown. 90-degree rotation, for example, in the E7, E5 plane will be a SU3 transformation and will give me this map. As an example, consider three complex octonionic combinations orthogonal to, let's say, 1 and even. So now, once again, I'll keep one direction fixed. Let's say E1, and because I want to get SU3, so I SU3 subgroup of G2, but now SU3 flavor. So again, keep one direction fixed, use the other 6 directions to get second and third generations. So under this map shown here, you can check that nu1 goes to nu2, like E4 is going to E6 like here, E5 is going to E2 like here, and so on. These transformations are generated by the following SU3 matrix, which interestingly can be shown to be made from Gell-Mann matrices like this. So we are really doing a SU3 transformation to get second and third generations, which will again feed into the Albert algebra. Important, SU3 flavor commutes with U1 electromagnetism. So all the three generations that get will be charge eigenstates. We now have a family. We have a family of three generations, and because charge is quantized, we have different families. The neutrino family, the down quark family, the up quark family, and electron family. And these are charge eigenstates. Right. So just shown explicitly for a fixed color, let's say a color that we have selected, this is the first generation set of states. Suppress the other two copies of D bar because it was in a particular color. Act these SU3 transformation to get second and third generation states. Thus, each family state is cycled through this sextet with E1 as assumed to be the complex number held fixed because that is what fixes SU3 flavor, faithfully realizing the three generations of an SU3 flavor rotation. So to put it in perspective, now we are not doing G2 transformations to get second and third generation, but only SU3 flavor transformations. And we have a definite notion of electric charge. Right. So once again, we make the Albert algebra for this left-handed family and in J, but now with the diagonals being electric charge. So 3 generations for one family, depending on what value of Q we take. Q is 0 for neutrinos, 1/3 for the down quark family. So this is for say down, strange and bottom, or up, charm and top, or electron, muon and tau lepton. Here we have made all those. Yeah, this is the second generation, this is the third generation. So for all the 9 charge fermions, we can make these 3 copies of the Albert algebra. We can do that for neutrinos also, but we are not talking of neutrino mass ratios today. So Q is the electric charge. XYZ give us the flavor triplet belonging to C cross O. And once again, we will calculate the invariance, trace this 2 form, this determinant, and find out the eigenvalue spectrum, which is now Q minus delta Q, Q plus delta. Q is the electric charge. Delta square is 3 by 8. This is the 3 by 8 we noted in the beginning table. Where does this 3 by 8 come from? It's not put by hand. What's happening is the norm of each of these states is 1 by 8. And this sum is 3 by 8. And if you put it in the cubic equation and you find the roots, you find that this is the spectrum. So the delta square 3 by 8 just emerges naturally. And we can now write a Jordan frame expansion for the left-handed sector. But now, importantly, an axis has been selected, which in this case, the electric charge was defined using E7 as the fixed axis. So no longer is there a triality symmetry which floats these eigenvalues across the Jordan frame. No, lambda 1 has to go with P1, lambda 2 has to go with P2, and lambda. So this is the emergence of electric charge and a selection of a particular vacuum on the left-hand side. Right. We can do the same exercise now for the second copy of the Albert algebra. This is where things begin to get interesting, because the 2 copies of the Albert algebra after triality breaking are not going to be identical. So how do we get the right-hand side? It turns out we can appeal to these interesting Clifford algebras, CL3 and CL7, which after CL8, there's a Bott periodicity. But up to Bott periodicity, CL3 and CL7 are the only 2 complex Clifford algebras which each have 2 irreducible representations. In the case of Clifford algebras, these are known as pinners. So CL7 has 2 pinners. CL3 also, which can be written as 2 copies of CL2, which interestingly decidedly have opposite parity. It can be shown that if one pinner is left-handed in terms of the wire spinners, the other one will be right-handed. So this is where a very nice and convenient way of getting chirality from Clifford algebras. CL7 likewise is made up of 2 copies of CL6 with relatively opposite parity. Omega is the split complex number made from the octonionic directions. And omega is what's responsible for giving relatively opposite parities. So we exploited this property of CL7 to make 2 copies of CL6. One, the left-handed copy, which I have already shown you. We got eigenstates of electric charge. And this is the second copy, which is right-handed. Using this second copy, construct one generation of right-handed square root mass eigenstates from CL6R with a trinification like this. Now we introduce this quantum number square root of mass. You can anticipate that U1 DEM will again have these eigenvalues 0, 1/3, 2/3, 1, like for the left-handed sector. But we will not call this electric charge. We'll call this square root of mass. What does that mean? Why do we do that? The physical motivation comes from experiment. If you look at, we know the electric charge ratios of the down quark, up quark, and electron. The electric charge of the down quark is 1/3 that of the electron, up quark 2/3, and this is the electron. And this is common across the three generations. It's remarkable that electric charge ratios are constant across generations. Within a generation, they are in the ratio 1 to 3. Actually, I should have emphasized that. If I go back a minute to an earlier stage, here, this is a derivation of charge quantization. Cole wrote that famous paper, quantization of electric charge from algebra. So this, we have she showed quantization of electric charge. It's manifest, yeah. There are only 4 charge ratios possible: 0, 1/3, 2/3, 1. It's a direct consequence of building one generation of states from CL6. I mean, we have no choice. This is how it should be. So, coming back to where we were, so this electric charge ratio that is observed in nature has now been derived from theory. From experiment, we find if we look at the masses of the down quark, up quark, and the electron is the lightest. Then the up quark and the down is the heaviest in the first generation. Their masses are within the uncertainties allowed by the experimental values. Their masses are in the ratio 1 is to 1 is to 4, 1 is to 4 is to 9, which means their square root masses are in the ratio 3 is to 2 is to 1, which is a flip of their electric charge ratios. The down has the smallest charge, 1/3 that of the electron, but its square root mass is thrice that of the electron. The up quark remains unchanged, and the electron's charge is thrice that of the down quark, but its square root mass is 1/3. So we say this is not a coincidence. It must be telling us something very fundamental, that square root mass and electric charge are related in a profound way. So the U1 DEM, what do we do with it? We say these, how do we attribute these numbers to the right-handed particles? The neutrino has the value 0 goes with the right-handed Majorana neutrino. 1/3 goes with the electron. So this is our new input. On the left-hand side, 1/3 was electric charge. It went with the down quark. On the right-hand side, 1/3 will go with the electron, 2/3 with the up quark, and 1 will go with down. So that is how we define the quantum of charge on the right-hand side to be square root of mass. We flip the position of the electron and the down quark. The electron has now become a triplet of SU3 prime, but SU3 color prime, but we won't gauge it. The down quark has become a singlet of SU3 color prime. So I hope you get the picture. If you have any questions, please stop me.
Yes, I have a question.
Yeah, please go ahead. Yes.
The exact ratio of those masses, 3 to 2 to 1, the ratios of the squared root of masses, it's not exactly 3:2:1. You had also this on the first or second slide, the comparison with experiment. I think that the
Yes, yes,
discrepancy is
yes.
like 2% or something like that. Okay,
Yeah, yeah. There is a range, and it could, in principle, be true that if future experiments improve mass measurements for the first generation, this theory could be ruled out.
okay, thank
Yeah,
you.
so I assume that it is 3 and then I derive 3:1 because that is obvious. If you could do it like Cole did for the left-hand sector, the mass quantization follows for the right-hand sector also. But you are right, this could be disproved in the future.
Okay, thank you.
Thank you. Any more questions? Right.
I guess I missed the. I apologize, Tejinder. This is Latham. I missed the first couple slides, but and what do you make of the other generations? I guess
Right. Very, very interesting. At this stage, the square root mass ratios are same for all three generations. That is how root m is defined. Just as electric charge is same for all three generations, root m is 1:2 is 3 for all three. But what is happening is the so-called electric charge eigenstates are not the same as square root mass eigenstates. If I ask what is the spectrum of masses for a fixed Q as seen from the left-hand frame, that's where the mass hierarchy will come from. Okay, physics-wise, what I'm saying is even when we measure masses, we are actually using electromagnetic fields to measure masses. In other words, we're using electric charge eigenstates to measure masses. And since the left-hand frame and the right-hand frame are different, as I will now show, that is why root m is not constant across three generations. In fact, if I was to go in the right-hand mass frame and try to measure electric charges using, let's say, gravitational fields related to mass, I will see weird mass ratios. Let's discuss this. So if you are not agree, please say so we can discuss this.
No, I'm interested to hear it. I just haven't understood it yet. But anyway, go ahead.
Let's see if it becomes clearer. Otherwise, we should discuss it. So I'm saying the ratios at this primitive level are the same, but we'll have on the left hand side a flavor basis and on the right hand side a mass basis. And these two bases are not the same, and that is the origin of the mass hierarchy. Okay. So, okay, the left-hand down quark and left-hand electron flip to a right-hand electron and right-handed down quark. So this is the trinification on the right-hand side. So on the left-hand side, we fix the axis E7. The corresponding thing here is E8. E8 looks unusual. E8 is actually just a short form notation for the product E1, E2, E3, E4, E5, E6, E7. Because we are in Cl7 split bioctonions, just two copies of Cl6. On the right-hand side, or you could think of it as omega times E7. So we have a fixed axis on the right-hand side, but it is not the same as the fixed axis on the left-hand side. So again, assuming the neutrino to be Majorana, I construct one generation of right-handed fermions, build the 8-state basic Cl6 for one right-handed generation, calculate eigenvalues of the square root mass operator now. U1 DEM is generated by this operator S. So these are 8 right-handed states, but now look at the identification. The electron is the triplet of SU3C prime, SU3 color prime, and that is why it has a square root mass of 1/3. The up quark remains at square root mass 2/3. the down quark goes to square root mass 1, and the same decomposition is there on the right hand side also. You can construct antiparticles which have a sign value minus root m. So plus root m and minus root m both will square to m, because the minus sign minus 1 square is 1. So we have derived square root mass quantization after chirality breaking. So why do the down, up, and electron have mass ratios of 149? We derive that as a mass quantization, just as coal derives electric charge quantization. We derive mass quantization, but just as a few moments ago while talking to Latham, I said, I emphasize again the same root m values for all three right-hand generations. But when we calculate the eigenvalues, we will see what is the difference. Okay. By
Could I?
repeating,
Oh,
yeah, please go ahead. Please go ahead.
okay. Just to try to make sure, try to understand. I'm trying to get the picture straight. And so the idea is you have two copies of the Albert algebra, one which is being called left and one which is being called right. And what is the connection between that and left-handed spinner versus right-handed spinner?
Yes,
Is there a connection, or
that's a very good point.
should I think of them as independent
No,
notions of left
they are
and right?
related to that. So if I take a spinner for, let's say, for 3 generations, I write it as a direct product of the Dirac part, which controls the chirality, and this internal space part, the J3OC part. So the one J3OC goes with the left-handed spinner, the other J3OC goes with the right-handed spinner. And before the Higgs couples the left and right-handed sector, I'm saying the left-handed states are calling them flavor eigenstates, right-handed states calling them square root mass eigenstates. Eventually, there are two Higgs in the theory. The standard model Higgs will give mass to left-handed particles, and a new Higgs will give electric charge to the right-handed particles. But there's a deliberate reason for calling these left-handed and right-handed, because I couple them separately to the two chiral spinners. Does that look okay? No.
Well, so the thing I'm confused about is, for the left-handed guys, there's 3 times as many down quark states as electron states, because the electron is a singlet and the down quark is a
Yes,
triplet.
yes.
And that agrees with the fact that we think there's three left-handed down quarks for every
Yes.
left-handed electron.
Yes.
But then what do I make of the right-handed side, where it seems
Yeah,
like you have
okay. So right
three
now
right-handed electrons for every right-handed
I'm
down
making a
quark?
safety clause. I don't want to gauge the SU3 color prime. The only force interaction that is important on the right-hand side from dynamics is U1 dark electromagnetism, which gives me these different root m values. I don't want to make for dynamically, the electron is a triplet of SU3 prime. We could do that, but I think that will get into trouble with phenomenology. So you
Uh-huh.
notice,
But I mean, even if you don't, maybe setting aside gauging it, what about just counting degrees of freedom? Like we only observe one left-handed electron for every one right-handed electron, or only one right-handed for every one left-handed,
yeah.
not
So
three.
that is true, but can I say if I don't gauge it, then I won't know that there are 3 copies, right?
Well, I think like there's experiments. For example, thermodynamics is sensitive to how many degrees of freedom there are. Or in we see color transitions between 3 different right-handed Dirac neutrino states. Three different Dirac down quarks. I mean, sorry.
Yeah, but is that not because I have QCD, I have a gauged interaction? No, I agree. This is a delicate point. by putting the electron in a triplet on the right-hand side, I am trying to get out of trouble by saying that I won't gauge the color prime interaction. But go ahead, say what you have to say. If you I mean, to my understanding was that this is not ruled out a priori.
I think there's very well with the I guess QED times QCD matches observations very well, and in that
Right.
situation, there's three Dirac
But
neutrinos
can
and
I
three.
not trivialize this SU3C prime? See, I'm not using it in any way. I'm only using U and dem.
Uh-huh. Well, I don't know. Yeah, I mean, sorry, I don't want to interrupt too. I mean, I must say I'm very interested in getting the numerology right. So I'm just maybe there's some correct interpretation. There's some way to interpret it all, and that
Okay.
I'm just
So,
confused about how
so
it works.
let's say to be on the safe side, I'm making an assumption that the electron triplet does not get me into trouble. Let's say I'm making an assumption. But if that can be ruled out, then of course we don't have a case.
Uh-huh.
So, but why do I need to put it there? Because I want to make the electron lighter compared to the down quark.
Right.
This is one, and since that this 1-to-3 ratio for square root masses is allowed by data, and since by doing this, I seem to get towards observing the observed mass ratios, I mean, I went ahead with it.
Yeah. Okay. But please go ahead. Yeah. Anyway,
Okay,
I'll
great.
keep thinking about it.
Michael, I'll need some 15 more minutes, please, if you don't mind. Okay, I'll go on. We'll get right. So
Yes, by all means, carry on. Take as long as you need to
yeah,
do that.
great. So I'm at the 22nd slide, so I have to. It ends at 30. So what we can do for the second Albert algebra, which is instead of electric charge, we have square root of mass. We can once again play the same game, write three flavor generations, constructed in a way very similar to the left-hand side, the second and third generations, with root m being constant across generations, but varying across families, taking values 0 for the neutrino, 1/3 for the electron, 2/3 for the down quark, 2/3 for the up quark, and 1 for the down quark. Once again, find out the spectrum by solving the cubic characteristic equation. And now this is the spectrum in the same Jordan frame basis as the left-hand side. The spectrum is root m plus delta. There's a flip of delta sign. Root m plus delta, root m minus delta. Delta square is 3/8. XR is lambda 1 P1, the same Jordan frame as before. And but lambda 1 is now the largest of the three eigenvalues. And here this is capital XL. If this is XR and XL was for the left-hand side, this should be capital XL, it's a typo. Little s stands for square root of mass. It's a short notation. There's a relation between the right-handed Albert algebra and the left-handed one. Earlier they were equal, right? Before triality breaking, they were equal to each other. But now there has emerged this non-trivial relation. And notice that this spectrum is different from the left-hand spectrum. Suppose I look at the down quark. Down quark would have been 1/3 minus delta, 1/3 and 1/3 plus delta on the left-hand side. Now it is 1. Instead of 1/3, 1. 1 plus delta, 1 minus delta, as opposed to the left-hand side, 1/3 minus delta, 1/3. And similarly, there's a flip for the electron. The up quark stays unchanged except for this plus minus delta flipping positions. The up quark stays. So there is an interchange taking place between the down family and the electron family. Okay, so now getting closer to understanding how the ratios arise. I define something called the symmetric cubic irrep of SU3 and the so-called Dinkin swap. Okay, so the proposal is that firstly, flavor eigenstates on the left-hand side are not square root mass eigenstates. So what was for a given Q, this might help a little bit to the understanding what Latham was asking. For a given Q, the mass spectrum is now root m plus delta, root m minus delta. You see what's happening. Either I can expand Q in the Jordan frame for a fixed root m, or I can stay in the flavor eigenstate basis. So now this is the answer. Why it is not root m for all three generations? Because the two left bases and the right bases are different from each other. So this is the origin of the mass hierarchy. Before triality breaking, if you had a situation like this, the root m floats. You cannot say that I have three different families. There are three identical generations. So one of the root m stays put. The center is what it was before I went to this particular Jordan frame. So that tells us that for one generation, say the first generation, I will still get the mass ratio 1 to 2 to 3 because of this center. Basically, it's the trace. The trace is different for the three generations. So for one generation, we'll retain the ratio 1 is to 2 is to 3 for the masses. But the second and the third generation won't do it. That's the origin of the mass hierarchy. It can be argued that mass ratios are not trivial ratios of these so-called Jordan eigenvalues. I might think I just make two ratios out of this. I should get mass ratios. But there's a reason why it is not like that. It has to again go do with the triality symmetry, because earlier we were permuting all the three eigenvalues and any sensible ratios would come from degree 3 monomials. That property is still preserved. We will make mass ratios from degree 3 monomials made from these three eigenvalues. Let us label them A, B, C in order. A is the smallest one, B is the middle, and C is the largest. So what are the different degree 3 monomials I can make from A, B, C? They will be of this form: A to the power P, B to the power Q, C to the power R, with P plus Q plus R equals 3. How many of them will be there? 10. 10 of them. Now, which 10? That's shown in this triangular diagram. A cube, B cube, C cube. Mixed ones, A square C, AC square, A square B, AB square, B square C, BC square, and at the center of this equilateral triangle, ABC. So these are the 10 monomials of degree 3 of this form. And it turns out that they belong to this so-called sim cube rep of the fundamental 3 of SU3 flavor L. What does it mean? Take a tensor product of three reps, fundamentally reps of SU3, that breaks as 10, 8, 8, 1. This is known to particle physicists. This 10, the so-called decuplet, is this sim cube 3 to which these 10 monomials belong. So ABC are the different Jordan eigenvalues. Our task is to find out where, for example, in these 10 points, which one, let's say, is the down quark. Suppose the down quark is here and the strange quark is at ABC. I will argue that the ratio of the square root mass of the strange to down is ABC divided by A square B. which is C by A. Okay, so that's how we'll make ratios. If you want to make a ratio of A squared C by A cube, that is again C by A. You want to make the ratio of C cube by BC squared C by B. Turns out that there are only three different fundamental ratios. Define edge operators E, B, and C. This actually related to group theory. This will be the SU2 subalgebras of SU3. What does the edge operator E do? It moves parallel to this axis A cube, C cube. This is the edge operator E. What does it do? It takes a weight PQR and sends it to P minus 1 QR. It eats a A. It eats a A. It gives a C. Eats up a A, gives, so for example here, A square B to ABC, reduce one A, increases C. The edge operator E does this. The edge operator B eats a A and gives a B. So that's what B is doing. Eats a gives a B. So this is the edge A to B. Left edge meaning from the left side to the center. This is the endpoint edge, left edge to right edge, A to C. And the center, the C edge operator moves like this. I'll just argue these are actually these are related to the 8 generators of SU3FL. The two Cartan generators label the different locations through the two hypercharges, T3 and Y. These are flavor hypercharges, not electroweak hypercharges. The 6 non-Cartan generators are E plus E and minus E, C and minus C, B and minus C. These are the root vectors of SU3, which go from one weight to another. So they have a nice group theoretic meaning. Our job is to identify which particle is where, and once I do that, I take the ratio, that is the derived square root mass ratio obtained from these eigenvalues. Okay. So to make the triangular diagram, so this is a weight diagram of SIM3, the 10 entries. This is the weight diagram and the root vectors. So let's define these Cartan weight root vectors and SU2 subalgebras. Introduce three bosonic modes A, B, C, the so-called Schwinger bosons in the SU3 case. Define normalized basis states of SIM3. So I am formalizing that triangular diagram by writing a occupation state depending on the weight. So if there is, depending on the weight of A, this creates A, this creates B, this creates C, and you make degree 3 monomials as kets in a three-state basis for a particle satisfying these conditions. And the Cartan generators can be easily shown to have these eigenvalues depending on the occupancy of A, B, and C at a monomial. So these label the 10 weights. The other 6 generators of SU3 define root vectors and the 3 edge operators. So these are related to the non-Cartan generators and give rise to the 3 SU2 subalgebras like this. So for example, given a flavor basis A, B, C, the B operator gives rise to one SU2 subalgebra like this, where NA, NB, and NC are the corresponding number operators. So just to say that there's a rigorous meaning to these edge operators. J plus minus are defined in the standard way using the Gelman basis. Thus, the triangle diagram of SIM3 has a simple interpretation in terms of the generators of SU3 and in terms of the root vectors. And it can be shown because of this same Klebs-Gordon coefficient appearing everywhere, that the ratios of two monomials only depend on the values A, B, C. They don't depend on any intermediate coefficient which can be normalized out. Okay, so last thing before we move on to deriving the ratios is the so-called Dinkin swap. There's a group theoretic way of mapping the left-hand electron family to the right-handed down quark family and the left-handed down quark family to the right-handed electron. So in other words, remember, we have done a 1 to 1/3 flip between the electron family and square root mass. On the left-hand side, 1 is the electric charge of the electron, 1/3 is the electric charge of the down quark. On the right-hand side, 1/3 is the square root mass of the electron and 1 is the square root mass of the down quark. So this flip, which we have already assumed, will play a decisive role in determining the charged lepton family mass ratios given the down quark family mass. So given the down family mass ratios, the charged lepton family mass ratios follow from this flip, which can be formalized. Maybe what you do is you flip two of the roots of SU3. So there's the root vector space is 6-dimensional. And if alpha 1 and alpha 2 are the simple roots, we can make the weights of the fundamental 3 in terms of these fundamental weights omega 1 and omega 2. Eventually, it amounts to interchanging the edge operators E and B and sending C to C inverse. In other words, if you have A square B, where the down quark will be, the electron will be at A square C. This remains unchanged, and whatever particle is at C cube, actually this will be the bottom quark, this will go to the tau lepton. So formally, I haven't shown you a proof, the 1 to 1/3 flip from the left to right hand side is in the weight diagram obtained like this. Okay, so I think so soon now, so finally we can talk of mass ratios. I have to find a way of saying which particle is where. So we recall where on the SIM3 diagram do the elementary particles lie? Recall ABC are the family dependent Jordan eigenvalues. Q, so S is root m, square root of m. For every Q, square root of m minus delta, S and S plus delta, S is square root of m, is the same as this object. Mass ratios are to be made as ratios of degree 3 monomials after determining at what monomial does a particular elementary particle lie. Here I propose a minimality principle that the second generation should sit at ABC democratically. So I will make a ladder for each family, ladder made of rungs. Like these weights are the rungs and the edge operators are is what the jump in the ladder. The second generation sits in the middle. So the strange quark, the charm quark, and the muon, the middle particle in each family, are sitting at ABC. I will make a ladder assuming that if I want to come to ABC, I should satisfy these conditions. Monotone ascent in C. I must reach the highest weight starting from the smallest weight in such a way that when I move along the ladder, C should not decrease. Top hierarchy saturation. I should end up at either at C cube or at B cube. The A exponent decreases by at most 1 unit per step. That is, if I have to come to ABC, I can come from A square B in one jump because A has changed by 1. So since my strange quark, the second of the down family, is here, my down quark is fixed to be here because I have to make a shortest hop to reach ABC. I could start here, but the hop becomes longer. So my down will be at A square B. My strange will be at ABC. Lightest state should be A heavy and C light. That's why A is the smallest eigenvalue. So the down is here. And there is some thing curious about the top. I will come to that. So that fixes, this minimality principle fixes the down ladder to be A square B to ABC to AC square to C cube. So I'll show you that in a moment in a better diagram. Down is here, strange is here, and bottom is here. So here's the diagrams. So in the weight diagram, this is the down ladder. A square B to ABC, and with this C and E landing up at C cube, as shown here. The up quark family ladder again starts at A square B, goes to ABC, but now takes this other edge to B square C. So I don't go to the end point, so we can come to that in the question answer session. So the up ladder is here, A square B to ABC to B square C. The electron ladder obeys this so-called Dynkin swap that I just talked of. The E and the B edge have to be interchanged and B and C have to be interchanged. So if you look at it carefully, this is the down family ladder and this is the charge lepton family ladder. It's a reflection of this fellow with A and C, with B and C interchange. So this was A square B. The electron is at A square C. The muon is at ABC. And the tau lepton is at B cube. What is very important to remember, it can be argued, that this down to strange edge E, this is the E edge shown here, this edge is mapped to this edge, AB squared to B cube. So this is the muon to tau lepton edge, but because of this so-called group theoretic property of Dynkin swap, whatever is the ratio here, which you can read now C by A, the strange to down ratio will be C by A, where C and A are the eigenvalues from the down sector. Whatever is the ratio here will be mapped to the tau lepton to muon ratio. So now we can do the computation, derivation of mass ratios. A is S minus delta, B is S, C is S plus delta. And the down family, down strange bottom, starts at A square B, goes to the center, goes all the way up to C cube. So the strange to down ratio is ABC divided by A square B, which is C by A for the down quark case. So that gives you this number. You can repeat this exercise for bottom to strange. That is C cube divided by ABC. The strange is at ABC. That once you feed in these values gives you this number. The lepton family and the Dynkin swap. So this is the lepton family, and the muon is here, the tau lepton is here. The tau to muon ratio, because it is so-called Dynkin swap, must come from the down ladder. The strange to down ratio is mapped to the tau to mu. This is what we call a prediction, that this ratio is the same as the strange to down ratio. The muon to the electron ratio, because of the normalization, takes this value and gets multiplied by a normalization factor C by A coming from the lepton sector. I don't have time to explain it in detail, but I can do it in the comments times, discussion time. The up quark family, up charm and top, up is here, charm is here. The top doesn't go to a corner. This is something to be discussed. If you ask me, I can come to it. And so that gives us the charm to up ratio, ABC to A square B, that is here. And the top to charm ratio, B squared C by ABC, which is this fellow. And the first generation I had already argued, that is coming from the central trace value. And we have already derived that one generation will have 1, 2, 3. And this is now, you see, because of this Jordan spread. For a given charge, you have 3 different mass eigenvalues, and this is the end. So I'm really sorry I have hurried greatly in the end. I'm done. Thank you. So we won't talk right now about phenomenology comparison with experiment, but because I hope there'll be some discussion. So thank you very much, and apologies for overshooting.
No, I don't think there's any need to apologize to Jinder. It was all you needed, all of that time to get through such very dense material. This was absolutely fascinating. I'm not going to abuse the privilege of the chair. I'm just going to throw it open. I do actually have one question I'd like to ask a little bit later about SU2 and how you get GR into the picture, which you said you were just touching on briefly, but we'll come back to that. Who wants to have the first question? Who's I don't see at the moment any hands raised.
Yeah, burnt, yeah.
Oh, yes, sorry, there you are. I'm sorry, I do now. Right, Bernd, do you want to go first and then David?
Then David Jack. Okay. I have a basic question about the eigenvalues and the eigenvectors. You said because of triality, there's not the kind of specific link between a certain eigenvector and a certain eigenvalue. So you can swap the eigenvectors to different eigen. What would this mean for a measurement? Normally, I expect if I do a measurement, I have an eigenvalue which is associated to a specific eigenvector, and so that the system is in a specific eigenstate. But if this is correct, I can get an eigenvalue, but the system could still be in different eigenstates then.
Yeah, but that is before triality is broken. We live in a
True,
broken
before
symmetry universe. In a broken symmetry universe, you cannot apply the triality permutation. You are right. A particular eigenvalue goes with a particular eigenvector. But suppose you went to the
the early universe.
the early universe before triality is broken. You'll
Yes,
see a very different kind of universe. I cannot visualize it.
but basically, if triality is not broken, doing a measurement gives you the value of your observable,
But
but
I
it
would
does
say
not.
something more stark. If triality is not broken, we don't exist. There are no measurements.
There are no
Uh,
measurements at all. But in this case,
there's
only
no
conceptually.
classical apparatus with which to make a measurement.
There are no classical operator. Okay, you don't have any. Okay. Good. Then I
Yeah.
don't need to continue asking questions if there's no measurement at all. Okay, Mr. Jackson, go ahead.
Great, thank you, Michael. Thank you, Tejinder. Thank you very much for the talk. I'm not sure if this is a bit too of a tangential question, but I'll try. So normally in the standard model, we introduce mass terms through Yukawa couplings to the Higgs, and that's
Yes.
how the mass has a kind of kinematic dynamical effect. You introduce the kind of physical motivation for using these parameters in the Jordan algebra as masses because of the ratios. I think on slide 19, you see this 3:2 to 1 ratio, and that gives you the physical motivation. So yeah, I'm just wondering, is it clear to see how these parameters come to take on this dynamical physical?
Yeah, very good point. I'm sorry I didn't touch on that. Sorry, I cannot hear you. Your voice went.
In this, and how you relate the
Yes. So there is a Lagrangian at the back of the mind where the Yukawa is coupling to the, let's say, the chiral fermions. This X, the Albert algebra matrix X, enters there like a scalar field. because it affects through its invariant, the trace, the two form, and the determinant. The Yukawa couplings are precisely these ratios. So basically, there is a mass matrix, and these eigenvalues diagonalize it. In the flavor basis, you see this Jordan spread. So, for example, a Yukawa coupling for the down quark would be something like A square B. That would be the Yukawa coupling.
Right, but is there a way to see why these parameters have that kind of kinematic physical quality to them?
Yes, that's a very good. What are they doing? This is their real. X really is a mass matrix, you see.
Right.
It's a mass matrix which I'm trying to diagonalize in the right hand. In the right hand frame, I diagonalize it in a certain Jordan frame. So kinematically, these Jordan eigenvalues are just precisely those Yukawa couplings. I discussed this a bit in the paper. And
Right.
the Albert algebra enters through its invariance. So in other words, when the symmetry breaks and a vacuum is selected, the expectation value of X is really what is fixing the mass matrix. And the expectation value has these diagonal entries, which are these degree 3 monomials.
Right. And is the Higgs basically standard model, or did you mention the Higgs something else?
There should be two Higgs.
The two Higgs. So I think
Standard
right,
model
right.
Higgs and another new Higgs, which assigns electric charge to the right-handed particles.
Right. So that's also another prediction of the theory.
So one could say that there are two Higgs. The second Higgs is a prediction, and both Higgs are composites actually.
Right.
Yeah.
Okay.
Latham, if you are there, I would like to hear your criticism about, does it help? You were asking how, if root m is same for 3 generations, then how come there's a hierarchy?
So first of all, yeah, I really enjoyed the talk, and I'm very, I find the numerology on this table very intriguing. I suspect the naive interpretation where there's just, for example, one left-handed electron and three right-handed electrons. I believe that is ruled out experimentally.
I would agree with that. So my question is, even if I don't gauge the right-handed SU3, I still have a problem, you are saying, is it?
Yeah, like for example, something that's.
Well, I'm somehow thinking if it is not a force, then how would I know, you see?
How cosmology examples come to mind for me, but
Yeah. But I think they all require, to my understanding, a gauging of SU3. I looked at this a little bit in the literature.
What I mean is what I have in mind is that, when you're computing the number of degrees of freedom in the thermal bath in the early universe, and how it
Right.
changes, for example, from before electrons and positrons annihilate until
I
after
agree.
electrons and positrons annihilate.
But
That
suppose I make this SU3 C prime inert. You see, I've not used it anywhere. I've only used U1, the dark electromagnetism, and its eigenvalues. Nowhere have I made any use of these electron triplets. So I'm trying to, in some sense, make them inert, and so that, they're practically not there.
So you're saying maybe the left-handed electron only pairs up into a massive Dirac state with one of the three right-handed guys, and maybe the other two just don't couple to anybody or something like that.
Yeah, I would like to think that the three on the right-hand side are in some sense identical and indistinguishable because there are no gluons. There are no right-handed gluons which are doing some interaction or transformations.
Uh-huh. Well,
But your point is good. Your point is
yeah.
good. I need
Anyway,
to.
but it's very interesting. I'm gonna, you know, it is interesting to think about whether there is some slightly modified interpretation of what's going on
Yes,
here.
I agree. I agree. I agree. I will run into that SU3 color prime because of the trinification, but somehow the interpretation should be such that it is trivialized. I agree with you totally.
Or yeah, or say another thing to think about is that if there's I think there, you know, the fact that there are really three different colors of the right-handed neutrino,
Hmm.
you know, I think that is, well, that's definitely the assumption in a lot of tests that of QCD in both colliders and in lattice gauge theory. And so I
Three
think,
generations of right-handed, these so-called sterile neutrinos. Is that what you're saying?
oh, sorry. I apologize. I may have misspoken. I meant that in your model, again, the fact that there is three left-handed down quarks, three different
Mhm.
colors of left-handed down quark, but only one color of right-handed down quark. Is that right?
Uh, Again, that would depend on how I interpret this SU3 color prime.
Or, but
I want,
in other
I
words,
want,
leaving aside, I'm maybe by color, I was implying that it couples to a force, but I just mean in terms of just counting that there's,
yes.
so
But no, but again, what's eventually the Higgs has to couple both the left and right sectors so that they look like in the standard model. That has
yeah.
to happen, yes.
Yeah. So famously, the weak force does couple only to left-handed fermions and not to right-handed fermions. That
Hmm.
you see you know, that leads to, you see that as maximal parity violation in
And
observations.
that at least would come out properly here.
You're right, but with the strong force, you don't see that. You know, the strong force doesn't violate parity, so it
Yes,
couples the same to left and right-handed fermions.
yes. So yeah, so one way I was thinking this SU3 color cross SU3 color prime, both are unbroken, and some maybe that is where underlies the reason why QCD is not parity violating. But I have to think over that carefully. I mean, how the so-called strong CP problem might be getting solved because this other thing is present, SU3 color prime, and at the same time it has to be not gauged. I agree, those things.
Mhm.
I should write down the full Lagrangian, the Higgs coupling, and
Mhm.
next
Anyway,
time.
very thought-provoking talk. Thank you.
Thank you.
Yes, Veselin Yorgov, would you like to ask your
Yes.
question?
Thank you very much for very interesting talk.
Thank you.
Now, naturally, I'm wondering because of this kind of parallel between charge and mass.
Mhm.
But we know that the conjugate representations, antiparticles would have the opposite charge.
Yeah.
Then what happens here with mass? How do you make sure that the mass stays positive?
Square root of mass, if I take square root of m, I get plus minus root m. Plus root m is for matter particles, minus root m is for antimatter particles. There's something I did not mention, but it's there in the paper. Mass is the Casimir of the squared momentum operator. I should relate my definition of mass to square root mass to the standard mass Casimir. So if S is the mass of square root mass operator, I basically say S square should be related to the momentum So P mu is S to the power 4. So in simple words, if the square of root m is m, positive. Even if I take minus root m, its square is positive.
Mhm.
Am I getting through to you on it?
Right, but I mean, I would expect that there could be a combination that you have positive and negative square root of mass coming from two different particles.
So,
And that means that you can have actually overall negative mass object.
I would try to avoid that. I mean, I don't see a place for that because the mass Casimir is being defined as the square of my square root mass operator, which ensures that mass is positive. Square root mass may have a
Right.
positive.
I mean, because it's mass
Okay,
squared.
I see your
But
point. I see
I
your
mean,
point.
what happens? How do you make sure that when you construct a product of particles with different masses of different sign, square root of mass, that they don't appear with negative values?
Okay, if I measure the force dark electromagnetism, then I would see attractive and repulsive
Mhm.
forces depending on whether the both are positives. So if I have plus root
Mhm.
m and another plus root m, it should repel, like in
Right.
electrodynamics. So I'm saying the dark electromagnetic force is extremely weak. I have some estimate for its coupling constant.
Mhm.
Extremely weak, but it is responsible for mass quantization.
Okay,
But,
I see. Yeah.
but if I could measure dark electromagnetism, that would answer your question. I should
Mhm.
see repulsion.
Okay.
There's something like a anti-gravity. Uh,
Mhm.
General relativity, gravity force is attractive between m and m, but dark electromagnetism between root m and root m is repulsive.
Mhm. I see.
Yeah, Burnt asked. Yeah, oh, he said, okay, yeah. You're right, Burnt. Dark electromagnetism is like anti-gravity, but we have to keep it very, very low strength. Yes.
Mhm. I see. Thank you.
Thank you.
By the way, thank you
ask?
for the nice
Oh, I'm
talk.
so sorry, Bernard. Do you want to follow up?
I just wanted to thank Tejinder for the nice talk and the much information he provided us all. So you can continue.
Yeah,
No, I
Anuj.
was just going to say, in respect of that last point about the um, about the way that some kind of anti-gravity features in this model, um, without taking us too far outside, the framework of the standard model. One thing which you mentioned in passing was the connection on the SU2 side with general relativity. Very broad question, but how does the graviton feature in this whole framework?
Yeah, so I think that is, I think, a very subtle point. We think of general relativity as emerging from the breaking of SU2R
Mm-hmm.
as a classical effective field theory,
Mm-hmm.
which I will not quantize. The only thing that I will quantize is what I call the gravidem sector, SU2R cross U1 dark electromagnetism. We will quantize that. You see what I'm saying? That is like quantizing the electroweak sector.
Mm-hmm.
If I just try to quantize general relativity, I will get a non-renormalizable QFT, just like the weak interaction is non-renormalizable. But electroweak is a good gauge theory. SU2L cross U1Y is a good renormalizable QFT before symmetry breaking. Same way, SU2R cross U1Y prime is a good renormalizable QFT. So classical general relativity is emergent after symmetry breaking on the right hand side. But so now the graviton could possibly be, there's a spin 2 mode that I can get from SU2. But I think we have to be very careful. As a classical theory, yes, it's equivalent to a spin 2 theory. But we are not quantizing it. What we are quantizing is SU2 R plus U1 as a Young-Mills gauge theory. So I would be careful. What are the associated bosons there? I mean, they are very much like Young-Mills spin 1 gauge bosons. And I would be careful in talking of gravitons. We haven't detected gravitons. So I would leave it at that. And your thoughts, Michael?
No, except that I agree. It is a very, very subtle issue.
Yeah.
And I just wanted to see if this entire framework made contact with it, which in fact you've explained it does, though there does seem to be a bit of a fudge factor in there.
Bhavan is asking, is the spin 2 graviton a composite of two spin 1 vector
Yeah,
boson?
okay. So, like the Higgs in your model, it would be a composite.
But people say that there's this Weinberg-Witten theorem that the graviton cannot be a composite.
I was just going to ask about that because, yeah.
I'm not an expert on that. What Jose had told me, I don't know if Jose is still there, is that there is a spin 2 state you can make from from 2 copies of SU2. Jose, are you there?
So
It's okay.
I
Let's
think the theorem you refer to is very much based on standard quantum field theory and also on
yes.
local interactions and all of this. That very much depends on how your model describes interactions, and maybe there's a loophole, but I don't know. But it's just very much tied to the structure of quantum field theory as we know it today.
We have classical general relativity. We don't know what it looks like at the quantum level. It's an open field. So my preference is to work with SU2R cross U1 DEM, which looks nice. You see, it is a correspondence to the electroweak sector. So we should go ahead with it. It's a good theory, and maybe try to understand what is the phenomenology of SU2R cross U1 DEM, if we can come up with something there.
Something as we are talking about gravity, what is the structure of space-time in your model?
Okay. As for
this is also important for this theory because
for the purpose of this work, E6 cross E6, I take a space-time background as given. But this, I didn't talk about it. This E6 cross E6 is embedded in a E8 cross E8. Each of the E8 decomposes as SU3 cross E6. And the second E8 has actually a split complex number sitting in front of it. So both the two E8s together give SU3 cross E6 and omega SU3 cross the other E6. Today we talked of E6 cross E6, but this SU3 cross omega SU3 may be a possible origin for the emergence of space-time. I don't make 100% claim.
Okay.
So, and before triality breaking, we have something like octonionic space. We don't have ordinary space-time. We have a non-commutative space-time labeled by many copies. So each space-time point is replaced by an octonion.
Okay. So basically you replace real valued coordinates for spacetime by octonion valued.
Yes.
Okay.
Yes. Or you call operator space-time points. That would be a good way of putting it. Instead of C-number space-time points, operator valued space-time points.
But how do you derive the operators? For example, could it be multiplication operators of the octonions?
Could be a
multiplication operators of the octonions.
Yes.
Okay.
But today, for today's talk, I don't go there.
Sorry, this is just because of this theorem which prevents the graviton from being a composite. It's based on Minkowski, so classical Minkowski space-time quantum field theory.
For this talk, I took Lorentz symmetry, space-time, wild spinners as given.
Okay, if you do this, then you're running into conflict with this theorem by Coleman and Witten. So because if you have something like local interactions and Lorentz symmetry, you really have trouble with getting a composite graviton.
Yes, yes. Yeah, but I would say that until we detect the graviton, we can be a little cautious and conservative in assuming its existence.
True. Okay.
That's very interesting. Tejinder, I'm sorry, I have to be frank, I didn't quite understand your answer to the question as to how you see space-time structure emerging in this picture. Can you just run over that again? I understood the point about Octonian space, but I didn't.
Okay, so let's not think of SU3. Let's think of SU3 branched into SU2 cross U1. Leave out the U1s for a moment. So SU2 cross omega SU2 from the two EAs. This together define the CL3 algebra of complex split biquaternions.
Okay.
And when they're restricted to the real sector, that gives rise to a six-dimensional space, Lorentzian space-time with signature 3,3. That has embedded in it two copies of 4D spacetimes, one which we identify as 3 plus 1 hours,
Yes.
and there's a
And
second.
the other is its dual, its shadow, which is
Yes,
the thing
yes,
you've been talking about many times in your model.
yes. So, because we have that split complex number, we can get a Lorentzian signature out of two compact Lie groups because there's a split complex number sitting there.
Okay, so that's the way you see it as emerging, but it's very kind of it's very high level algebraic way of thinking about the
Yes,
emergence
yes,
of
yeah.
space-time.
That's why today I did not want to go into the
Sure.
space-time part
No.
because, to my understanding, the mass ratios part seems very algebraic, largely independent of the dynamics.
Yes.
It is very much to do with the Jordan algebras and the breaking of triality symmetry.
Yes, it's a fascinating, very compelling picture. I mean, beautifully presented. It's a pity Anthony Lazenby is not here because he's always got interesting things to say about the Jordan algebras.
Yes, we
But,
missed him. Yeah.
and are there any further questions? It's been such a good discussion. It's a pity to curtail it. Are there any clarificatory questions that anybody has? Well, it seems not, and I think that's because you did such a very good and thorough job of presenting the framework.
Let's
Uh,
see. Some
It certainly generates a lot of, there are an awful lot of hairs started by this. I think we can return to this topic, I suspect, again and again.
we have to get particle phenomenologists interested in.
Yes. This tends to be, yes, the algebraic structure here tends to go way beyond the kind of thing that people interested in particle physics phenomenology
But
are
it is
comfortable with.
analytically not so difficult. Yeah, we have a 3 by 3 matrix. We are solving its characteristic equation, finding eigenvalues.
Well, thank you. I'll join in what George has just said in the chat, which is thank you for a really great talk.
Yeah, thank you
Echo
for
that
coming.
and tremendous. Let's continue the conversation. We're going to be back in 2 weeks' time, I think I'm right in saying, on the 3rd of
Indranil.
October.
Yeah, I should send out the notice. Yes.
And that's going to be Indranil.
Yeah, that should be a very interesting talk. The absence of dark matter in dwarf spheroidal
Yes.
galaxies.
Going back onto our Mondian wavelength.
Yes.
switching on multipolarity. Okay, and we're also hoping very much, of course, to hear from Abhay Ashtekar, who had been due to speak on the 3rd of October, but who's now, I think, planning to speak on the 28th of November?
Yes, 28th of November. We have free slots in November, so
Yes.
we are open to.
Yes, I'd like to talk to you about that because a couple of
Yeah.
possibilities.
Yes.
Well, thank you again very much indeed, Tejinder, for an absolutely fascinating talk. And thank you, everybody, for taking part in such a good and thoroughgoing discussion. All right.
Thank you
Take
for
care,
coming.
everybody. We'll see you again on the 3rd of October.